Welcome back to the lecture series on pattern recognition. In the last two lectures, we have discussed what clustering is, various real-time applications of clustering, and then we have discussed different types of clustering methods. So like hierarchical clustering, density based clustering, partitioning based clustering. So what is the basic idea behind these different types of clusterings are? So that's what we discussed in the previous two lectures. In today's lecture, we'll be discussing the partitioning based clustering method, the K-means and the K-Medoids algorithm. So basically we have already discussed the details about the K-means. In today's lecture we'll be discussing what are the limitations of the K-means clustering algorithm, and then so why do we need to go for the K-Medoids algorithm and how it overcomes or rectifies the limitations of the K-means algorithm. So that's what we'll be discussing. In addition to that, we'll be discussing one more density based clustering algorithm known as DBSCAN algorithm. That's what the plan for today's lecture. So in the previous lecture, we have discussed K-means algorithm in detail. So like how the K-means clustering works, the working of the K-means clustering. So given the set of objects, we choose K number of, if you are choosing your K value, so say for example 3 in this case, you are choosing K randomly selected samples from the given collection of data, and then you are assigning every data sample to the closest cluster possible, and then you are finding the mean of the cluster, and later on in the further iterations, so that mean will act as a centroid for the cluster, and you will be repeating the process for n number of times, or something like till the convergence, till it converges based on the convergence criteria you are selecting. So that's how the K-means algorithm works. So you can observe how the K-means clustering works. So in the initial iteration, so you are selecting one of the data point, randomly selected data point somewhere here, and somewhere here as the center for the clusters, and later on your cluster center will not be one of the data point. It will be the mean of yours. Say for example here all the blue dots form one of the cluster, the red dots form the second cluster, and the green dots form the other cluster, and the centroid is represented with the star symbol, and which need not to be the one of the data objects. So it is the mean that is formed with the set of set of data points of the cluster. So that's how the K-means algorithm works. And let's see some of the limitations of the K-means algorithm. And K-means algorithm is very much sensitive to the initially selected cluster centers. So if you observe, if these are the given data samples, and if you are assuming that these are the initial cluster centers that you are randomly selecting, where your K value is 2, in that case, so over the iterations, so these are the set of clusters that are formed. These are the 2 clusters that are formed when you apply the K-means algorithm. And say for example, instead of selecting these 2 as the initial cluster centers, you are selecting these 2 points as the cluster centers. In that case, over the iterations, your K-means form these 2 as the clusters. So you can observe what is the basic difference in these 2 algorithms. So the same K-means algorithm we are applying, and the same set of data you are giving as input to the algorithm, but the difference here is the initial cluster centers. Here these 2 are the cluster centers you started with, and here you started with these 2 points. In that case, so the final clusters, the only difference in these 2 cases is the set of initial cluster centers we are selecting. In these 2 cases, the difference is the initial cluster centers we are choosing. They are different. Other than that, the same K-means clustering we are applying, the input samples are also the same. But we ended up with the different sets of clusters when we choose these 2 as the initial centers. So we have these 2 as the clusters. And when we select these 2 as the initial cluster centers, then so these are the clusters we have got produced by the K-means algorithm. So that's how K-means clustering is very sensitive to the initial randomly samples we are selecting as cluster centers. That's one limitation of K-means, and the other limitation of K-means is it's very much sensitive to the outliers. So if there is any outlier in the input data, then K-means is very much sensitive to the outliers. For example, consider this case. Here this is the outlier sample, and when this data is given, and these are the original clusters that we expect. So this data actually is an outlier and it can be ignored, and we need not to make it as a part of the cluster, and we expect these two clusters to be formed by the, to be produced by the K-means or any other clustering algorithm. And when we apply K-means algorithm on this set of objects, then what happens is, because of this, because of the presence of this outlier, so the data, the clusters formed are these two. So this is one cluster and this is the other cluster. So instead of producing these two as the clusters, the algorithm is producing a different set of clusters, so which is not expected by the which is not expected. So that is how K-means is very much sensitive to the presence of outliers. This problem is more when we use the sum of squared error as the objective function. So to avoid the problems with the K-means clustering algorithm, K-Medoids clustering is introduced, and let's see how it works. In case of the K-Medoids algorithm, the K-Medoids algorithm actually is introduced to diminish the effect of the outliers that is actually present in case of the K-means algorithm, and this algorithm is proposed by Kmeans and Rousey in the year 1987, and the algorithm is also known as partitioning around Medoids. Actually we are instead of considering the mean or the center of the cluster centers, so we use what we call it as a Medoids. So that's how the algorithm is known as partitioning around Medoids. So we are basically partitioning the data around the Medoids. That's how it's named as partitioning around Medoids. Let's see how the algorithm works. So this is the basic principle of the K-means clustering. In case of the K-means clustering algorithm, given the input data, always if this is the cluster, then the cluster center, so the cluster representative, in case any cluster is represented with the, any cluster is having a representative point. In case of the K-means algorithm, this is the cluster representation, right, which is not one of the given data sample. So it is actually the mean of the data points present in the cluster. So it need not to be one of the data samples, because we are considering the mean of the data samples. Whereas in case of the K-Medoids algorithm, when we go for the K-Medoids algorithm, the cluster representative must be one of the data samples. That is the basic difference between K-means and the K-Medoids. Other than that, both work more or less in the similar lines. So the basic working principle of the K-Medoids algorithm is, instead of considering the center as a cluster representative, in K-Medoids we consider one of the object of the input data or the one of the object present in the cluster as the representative member for the cluster. So that is the difference between K-means and the K-Medoids algorithm. And the representative, the cluster representative point is called as a cluster Medoid, or we can even call it as simply as a Medoid itself. So if you consider this cluster, and these are all the data points that are present in this cluster, in case of the K-means clustering algorithm, so the cluster is represented with the mean, and the mean need not to be one of the data samples. Whereas in case of the K-Medoid, it is expected that one of the data points, either this could be the Medoid or this could be the Medoid, this could be this could be the Medoid. But it is not other than the Medoid, or the cluster representative is not other than one of the data samples. If you observe the problem limitation with the K-means clustering, K-means is very much sensitive to the noise, and this kind of cluster formation is only because of the presence of this outlier, and as we are allowing the mean as a cluster representative, and which is not the one of the data object, and if we don't allow such thing, so this kind of clusters would not have been formed. So that is how we insist that the cluster representative must be one of the data sample in case of K-Medoids. And now let's see the algorithm, how the K-Medoids algorithm works. So we select k random points similar to the K-means clustering. We select k data points from the input data as the initial Medoids. So now let's see how the K-Medoids algorithm works. The working of the K-Medoids algorithm. Similar to the K-means clustering algorithm, in K-Medoids also you need to select k random samples from the input data, and these k random samples of the input data, they act as the initial Medoids in the algorithm. So now once you have the K-Medoids, which are randomly selected samples, and we need to assign every data point in the data set to the closest Medoid, and to assign every data point to the Medoid, we can use one of the distance measures, and this distance measure can be any of the commonly used distance measure, and you can choose any of the measure depending on the type of the data you are using, or depending on the application you are using. And once that is done, the initial assignment of every data point to one of the closest Medoid, we need to repeat this set of steps for a certain number of steps, and as long as the cost is reduced, you need to repeat this process. When the cost is not reduced over the iterations, at that point of time we can stop repeating the iterations. And what we need to do in every iteration is, you have to select one of the Medoid, so that you call it as M, and you choose one of the random data point O, and which is not a non-Medoid, and you just swap M and O. That is, so you are making one of the non-Medoid as a Medoid, and you associate every data point and compute the cost. So once the cost is computed, you just check whether the cost is reduced by this reassignment or not, and if the cost is reduced, then you proceed with the swapping of the Medoid M and the data point O. That is, hereafter this data point O will act as a new Medoid in your one of the K-Medoids. Otherwise, if the cost is not reduced, then you just swap the M and O. That is, your M itself will act as a Medoid, O will not be the Medoid for your algorithm, and you need to repeat this process till the cost is reduced. And now let's see an example of K-Medoids. How do we execute the K-Medoids algorithm? So consider these set of examples. I have 10 examples, these 10 samples, and every sample is having two attributes. It is represented as x1 comma x2. Say for example, the first data point is represented with 7 comma 6, and second data point 2 comma 6, so on and so forth. So these are the set of data points that are given to us, and we are assuming that the k value is 2. That is, we need to select two of the samples as the Medoids, the initial Medoids, and assume that we are selecting 3 comma 4 and 7 comma 4 as two Medoids. So similar to the K-means clustering, however we did in case of the K-means clustering, in case of the PAM or the partitioning around Medoids or the K-Medoids algorithm, we are going to choose k random samples from the given data. And in this example, I am going to choose this data point as the first Medoid, and 7 4, and that is this one. So that this is another cluster center, that is a Medoid. So these two will act as the Medoids for the algorithm, and let's try to assume that Manhattan distance is a metric that I am going to use as a distance measure. So because we need to assign every sample to one of the closest Medoid, so you need to assign this sample to either of these two Medoids. Similarly, you need to assign all these 10 samples to one of these two Medoids, right? And for that process, to assign every data point to one of the closest Medoid, you need to identify the distance measure. And to make it simple, I am choosing Manhattan distance, because calculating Manhattan distance is very, very simple compared to the other distance measures. And now let's assume that we are going to identify the Manhattan distance. So now let's see, identify. Given sample is 7 comma 6, so this sample is 7 comma 6, and the first cluster C1 is represented with 3 comma 4 is the first Medoid, and the second cluster is 7 comma 4. 3 comma 4 and 7 comma 4 are the two Medoids that we are selecting. So once these two are selected, you need to assign this to either to the first Medoid or to the second Medoid, and for that we are going to use the Manhattan distance as a distance measure. So let's compute the distance between 7 6 and 3 4. So the distance between 7 comma 6 and 3 comma 4. So how do you compute? Manhattan distance is simply the summation over the absolute distance between the corresponding elements. The summation of the absolute distances between the corresponding elements. So 7 minus 3 absolute value plus 6 minus 4 its absolute value. And what is it? It is 7 minus 3, it is 4 plus 2. So this is 6. So the distance between these 2 points is 6. The Manhattan distances. Similarly, you need to find the distance between 7, 6 and 7, 4 also. And if you find the distance between 7, 6 and 7, 4, so the distance value is 2. So this is the distance from 7, 6 to the first cluster is 6, and distance from 7, 6 to 7, 4 is 2. So these two are the distances I got. And to which medoid I need to assign the first data sample? It is to the second medoid. So that is because the distance to the second medoid is less, we need to assign it to the second medoid. And now let's see. So here these are all the distances I computed to the medoids. So for every data point I just computed the distances 6, 2, and for the second sample it is 3 and 7, and third sample it is 4 and 8, so on and so forth. That is how I computed the distance to every medoid. So now once the distances are measured, you need to assign, depending on the distance measure, you need to assign the samples to one of the medoid. So first sample to which cluster I need to which medoid I need to assign? That is to the second cluster. The reason is simple. So because the distance is low to the second cluster, second medoid, you just assign the sample to the second medoid. And here the second sample is assigned to C1. That is the first medoid. So then here first medoid. Here it is second medoid. The next sample, of course, it's already the medoid and it's representing the second medoid. So assigned to the second medoid itself. And this one to the first medoid, the second medoid, and this is also to the second medoid, and of course this is the first medoid itself. So that's how you just assign every object to one of the medoids, one of the two medoids. So the assignment is done. So once this is done, so you can observe that the clusters that are formed at this iteration, at this stage are, so you can observe this. So this is C1, that is the second object, 2, 6, then 8, 5, and 7, 4, and you have 6, 2, then 7, 3, 6, 4. So these are all the data points that form one cluster, and these are all the other points that are in the other cluster, that is cluster 1. So cluster 1 and cluster 2 are formed. So the initial cluster formation is over. Every data sample is assigned to one of the medoids, and now after this you need to compute the cost. So with this assignment, so what is the cost that is involved? That you need to identify. How do we identify that cost? So the cost can be identified as, so the cost you can identify it as sum of the distances from the non-selected data points to the selected data points. So that value, the summation of that value will become your cost, the total cost. Now let's see. So here, because of this assignment of the first data point 7, 6, let's change. So because of the assignment of the first object to the second cluster, the cost involved, what is the distance to the distance from this object to the second cluster? It is 2 points, right? So you just consider the value 2, and I think I better use this 2 plus the second object. When you consider the second object, to which cluster you need to assign? You assigned it the cluster 1 itself. And what is the distance? It is 3. So it's plus 3, and it's simply you can figure it out like this. So it's a minimum of the distances between the clusters, minimum of the distances between the data points and the clusters assigned. That's how you can simply take the distances. Here it is 4 plus 2 plus 0 plus 4 plus 3 plus 1 plus 1 plus 0. So if you just sum up all these things, the cost is 20. And this is the cost that is incurred because of this assignment. And now let's proceed and do the swapping. The next step in the algorithm is you need to swap the medoid, one of the medoid. So you just select one of the medoid and swap that with one of the non-medoid. And I am going to choose the 7, 4 medoid, and instead of that medoid I am going to choose the non-medoid as 7, 4. So now this is the non-medoid, and I am going to choose this as the medoid. So instead of that 7, 4, I am going to choose 7, 3. And because of that, what is the cost that is incurred? Again, you need to repeat the process. So the same way, however, we did. So when 3 and now the medoids are 3, 4 and 7, 3. And because of this medoids, what is the cost that is incurred? So that we need to calculate. So the process is the same. So you just identify the distance measures from every non-medoid points to these two medoids, both the medoid points, and then assign every object to one of these medoids and then compute the cost. And because of this assignment, the cost incurred is 22. And what was the earlier cost? It is 20. So is the cost is reduced or increased? It is increased. Because the cost is increased, this swapping of the medoids is not a wise decision. So better don't use the 7, 3 as a medoid, retain 7, 4 as a medoid itself. Because the cost is not reduced, you can stop the process here itself. Or if you want, you can try all the non-medoid points and compute the cost till the cost is reduced. That is how you can repeat the algorithm and you can get the final clusters. So here, if you observe the total cost when 7, 3 and 3, 4 as the medoids, the cost is greater than when the medoids are 7, 4 and 3, 4. So because of that, we retain 7, 4 as the medoid instead of 7, 3. So 7, 4 and 3, 4 as the medoids. And so if you are interested, you can repeat the process, otherwise you can stop the process. And finally, these are the two clusters that you are forming. So here in this case, your cluster center is 3, 4, that is a medoid, and 7, 4 is another cluster center. And these 4 points form one cluster and these 5 points form one cluster. So which is comparatively better set of clusters. And now let's see the difference between K-means and K-medoid, how they are different. So in some ways they are similar and in some way they are different. So how they are similar? So the way you are choosing the K value. So like before you start executing your algorithm itself, you need to have the K value as predefined. In both K-means and K-medoids, your K value has to be predefined. So in that way, both K-means and K-medoids are same. And also, you need to choose the initial cluster centers also, both in K-means and K-medoids also. In K-means, whatever you are selecting, you are calling as cluster centers. In K-medoids, whatever you are selecting randomly as cluster medoids itself. And then, how they are different. K-medoids is more robust because it's not much sensitive to the outliers. It can deal very well with the outliers, because you are insisting that one of the data point must be the medoid. So because of that constraint, it is much it can handle, it is much robust when compared to the K-means algorithm. And now the time complexity, coming to the time complexity, the time complexity of K-means algorithm is order of K into N into D, where D is the dimensionality of each data object and N is the number of data samples and K is the number of clusters. And in case of the K-medoids algorithm, the time complexity is order of K into N minus K whole square, where K is the set of medoids and N is the number of data samples. And now let's see what are the variations of the K-medoids. The problem with the K-medoids is whatever we discussed so far. The problem with that PAM algorithm, partitioning around medoids algorithm, is it cannot scale well when the data set size is too large. That is the problem, that is the limitation with the K-medoids algorithm because of the high computational complexity. To avoid that, there are certain applications or the variations of the PAM algorithm were introduced which can deal with the large data sets, which can scale well with the large data sets. Those algorithms are Clara and Clarence. So Clara stands for clustering large applications and Clarence stands for clustering large applications based on randomized search. So these two are the variations of the PAM algorithm that we just discussed, and they can very well deal with the large data sets. And Clarence is a much better improved version of the Clara algorithm. That's how we can form clusters using the K-medoids algorithm, and K-medoids algorithm is much robust than the K-means algorithm because we are insisting that one of the data point must be the cluster representative. Because of that constraint, it's much robust than the K-means algorithm. And now we have seen two different types of algorithms, that is the K-Medoids and the K-Means algorithms. These two are the types of partitioning. They comes under the category of the partitioning algorithms. And now in the rest of this lecture, we'll be discussing density based approaches. So let's see few of the density based approaches. And before proceeding further, we will try to understand what the density based clustering algorithms are, and as part of the density based algorithm, we'll be discussing the DBSCAN algorithm in detail. And to understand the DBSCAN algorithm, we need to have proper terminology, and first of all we'll introduce that terminology, then later on we'll discuss the DBSCAN algorithm. So let's see how the density based clustering algorithms works. So basically the density based algorithms are introduced with the basic idea that, so in the more dense regions, in the dense regions there is a possibility of having the clusters rather than the sparse regions. So with that in mind, the density based clustering algorithms work. And the problem with the partitioning and the hierarchical algorithms are they can work very well when the data or the clusters are of type vowel shaped. The partitioning and the hierarchical types of algorithms, they can very well work with the spherical shaped clusters, but they cannot do well when the type of data is either oval shape or the S-shaped clusters. So in that case, both partitioning algorithms and the hierarchical algorithms, they fail. In that case, these density based clustering algorithms, they work very well even when the shape is any arbitrary shape. So it can be oval shape, it can be S shape, it can be any zigzag shape also. So it can deal with any different shape. So that is the advantage of using the density based clustering algorithms. And to find these arbitrary shaped algorithms, so we can model the clusters as dense regions, and we have some of the popular density based clustering algorithms as DBSCAN, optics, and also DENCLU. And the basic idea of the density based algorithms are, so the idea is basically in the dense regions there is a possibility of having the clusters rather than in the sparse regions. That is how we are focusing on the dense regions than the sparse regions. If you observe, so given this data, where is a possibility of having the clusters? So there could be a possibility of having, one cluster here because it is dense, and there is a possibility of getting one more cluster here, and there is a possibility of having one more cluster here, right? And to deal with this kind of arbitrary shaped clusters, the density based clustering is used, and the cluster is defined as a maximal set of densely connected points. That is how the cluster is defined in case of the density based clustering algorithms, and it can very well deal with the outliers, it can very well deal with the arbitrary shaped algorithms also, arbitrary shaped clustering. And the method that supports this density based clustering is the DBSCAN algorithm. Yeah, to understand the density based algorithm, we need to understand two parameters, the epsilon and the minimum points. So in case of the epsilon represents the maximum radius of the neighborhood. So both Kmeans and K-Medoids, they work on the principle of neighborhood. So you are assigning, how you are assigning in case of the K nearest neighborhood. In case of the K-Means or the K-Medoids algorithm, you are assigning, if you have two different cluster centers, you are assigning a point to the cluster which is close to this data object. If you assume this is one cluster center and this is another cluster center, when you are given one data sample, this is a data sample during prediction, and you will be assigning this sample to the closest sample, that is to the nearest neighborhood, right? So to this nearest neighborhood, whichever is the cluster that is assigned, to this example also you are assigning to the same cluster. With that idea, the K-Means and the K-Medoids work, and the same principle can be extended here also. For that, the epsilon is defined, and the epsilon represents the maximum radius of the neighborhood. If you observe here this example, in this case you can see that, so I am defining this as the radius of this point, the radius of this point Q. So this is the Q and this is the epsilon, And what are the nearest neighborhoods for this Q now? Because I defined the epsilon, and this is the radius that is covered with this epsilon, and all the points that fall within that region, they only form the nearest neighborhood for this Q. And similarly, if you observe this point P, and for this point P, this is the epsilon radius. You can observe this figure, and this is the epsilon radius, and whatever the points that fall within this epsilon radius, those are all the points that form the nearest neighborhood. So that is how you can define the nearest neighborhood and the epsilon neighborhood. And let's see what are the minimum points, and how many ever number of minimum points you are expecting within this region, they are called as the minimum points. Say for example, how many points you are expecting here? We'll see that in the next slide. Yeah, so we just now discussed what the epsilon neighborhood is. Maybe in mathematical terms, you can represent the epsilon neighborhood like this. So this n stands for the nearest neighborhood, and epsilon is the radius that you are going to use, and p is the point you are representing. For the point p, what is the nearest neighborhood when epsilon is the radius that you are using? And within this epsilon radius, what are the nearest neighborhoods? What are the set of nearest neighborhoods for the given element p? So that is the set of all the elements, in the given data set. So whose distance is less than or equal to this epsilon, that is, which are falling within this radius of epsilon from this object P, they all form the nearest neighborhood. Say for example, here if you consider P, and this is the epsilon, if you assume this is the epsilon radius, in that case, so this element, this element, this element, this element, all these four elements form the epsilon neighborhood. So if you write this as something like A, B, C, D, maybe I can write it as set of elements, so A, B, C, D. So this is the epsilon neighborhood for P. And if you change the epsilon value, then of course the set of nearest neighborhoods change. Say for example, I am changing my epsilon to this. In that case, what happens? So this element and all the elements that are here in this radius, they all form the nearest neighborhoods for the point P. And now let's see what high density region is and what low density region is. And you can call a region as a high density region if the epsilon neighborhood of a point is having the minimum number of points within that region. Then you can call it as high density region. And if it is not satisfying that, then you can call it as a low density region. And here you can observe that the density of P is high. Here if you observe, what is P? P is the data object, and the density of the object P is high because the number of minimum points in that region is 4. Observe here, how many nearest neighborhoods are there in the region of P? 1, 2, 3, 4. So the number of minimum points are 4. And similarly, if you observe for the point Q, so what is the density of the point Q? It is only 1, 2, 3. So the number of points in this region is 3. And the density of this Q is low. So you can say this is low, but for the P it is high. And you can even represent the epsilon neighborhood of every data point. What is epsilon neighborhood of a data point? It is all the sets of elements in the data set which fall within the radius of the epsilon. To understand what the DBSCAN algorithm is, we should understand some of the terminology, the core point, border point, and the outliers. So let's define what the core point, border point, and the outlier are. So core point is the point, any data point in the given input data which is having enough number of elements in the core point is any data point which is having more than the minimum number of points within the epsilon neighborhood. If you observe this, here this point is a core point. What is the reason? If you assume that the minimum number of points is something like 5, in that case how many minimum points this element is having? 1, 2, 3, 4, 5. Even if you include this, it is 6, right? So the minimum points itself is 5, only 5. So I have 6 points in the nearest neighborhood of this point. Now I can call this point as a core point. And now consider this element. So if you observe this element, and if you observe the radius is this epsilon radius, and how many minimum points are there within the region? I have only 1, 2, 3, 4 and 5. Of course this is also again it is 6, right? So here I can call this also as a core point. And now consider this element. So for this element, how many elements? This is the region of epsilon neighborhood, and 1 2 3 4 5 6 7 elements are there in the nearest neighborhood. So this also, it can be called as a core point. And now consider this object. For this object, this is the epsilon neighborhood that is marked, and how many elements are falling within the neighborhood? Only 3. And that 3, the nearest neighborhood number is much less than the minimum number of points. Because it is less, you can call it as a, so the nearest neighborhood element, the number of nearest neighborhood elements is much less than the minimum number of points. But there is a catch here, because this is one of, this element is in the nearest neighborhood of the core point, one of the core point. If you observe, this is the core point, and for this core point, this element is the in the neighborhood, nearest neighborhood. That is how this element can be called as a border point. So border point is the element which is in the nearest neighborhood of the core point of some other core point. So such elements are called as border points, and the outliers are the points which are neither core points and nor border points. So now everything is set ready. One more, few more terms we need to understand. They are related to the connectivity. So one is directly density reachable, whether the element is directly density reachable or not, or whether the element is simply density reachable or densely connected. So these 3 terms we need to define. Let's define that. So let's understand what directly density reachable point is. So you can define one point P as density reachable from a point Q, and if P is in the nearest neighborhood of the Q. So in that case, I can call it as a directly density reachable. So here you can see that P is in the nearest neighborhood of Q with respect to the epsilon value and also the minimum points. If you consider here, so Q, if you consider Q, this is the epsilon nearest neighborhood, and epsilon is 1 centimeter we are considering, and the minimum number of points are 5, and in that case P is within the epsilon nearest neighborhood of Q. In that case, I can call P as directly reachable from Q. That's how we can define directly density reachable, and this directly density reachable is asymmetric. If you observe, P is directly density reachable from Q. So because P is in the nearest neighborhood of Q with respect to the minimum number of points and epsilon, whereas if you consider Q is not in the nearest neighborhood of P. So for P, this is the region, and it is not in the nearest neighborhood of Q. That is how Q is not directly density reachable from P. That is how we can define directly density reachable. And now let's see what density reachable is. So we can define density reachable like this. A point P is directly reachable from, a point P is density reachable from the point Q if there exists any intermediate point P1 which is directly density reachable to Q, and P is in turn is directly density reachable from P1. If you observe, for Q, P1 is directly density reachable and P is directly density reachable to P1. So if that chain is valid, in that case you can say that P is density reachable to Q, but P is not directly density reachable to Q. That is a point to be noted. P is not directly density reachable from Q, but P is density reachable from Q. P is directly density reachable from P1. So you can define it like this. So a point P is density reachable from a point Q with respect to the epsilon, given epsilon and the minimum number of points, when there is a chain of points P1 to Pn such that P1 is directly density reachable from P, P is directly density reachable from P1, and P1 is directly density reachable from Q, so on and so forth. So if that is the case, you can say that P is density reachable from Q. You can even call it as indirectly density reachable also. And now let's define one more term, density connected. So two objects P and Q are density connected if there exists one more term one more object O, when from O P is density reachable and from O Q is also density reachable. In that case you can say P and Q are two different objects which are density connected. And now everything is, the terminology is defined, everything is set ready to understand the DBSCAN algorithm. And DBSCAN stands for the density based spatial clustering of applications with noise. Basically this DBSCAN algorithm is designed to deal with noise and can form any arbitrary shaped clusters. That is how the name is given as density based spatial clustering of applications with noise. Yeah, let's see how we can define this DBSCAN algorithm. So DBSCAN algorithm works on the principles of the density based notion of the clusters, and cluster in the case of the density based clustering, the cluster is defined as a maximal set of densely connected data points. That's how we define cluster in the case of the density based clustering algorithms. And these are very good. This DBSCAN algorithm is very good at designing arbitrary shaped clusters, and they can very well deal with the noise also. And we already defined what border point is, core point, outliers are. And we already defined the epsilon and the minimum points also. And now let's see how the algorithm works. So initially you need to select one of the point P. You can arbitrarily select that point P, and you can retrieve all the points that are density reachable with respect to the epsilon and minimum points from this point P. And if P is a core point, if P is identified as a core point, then a cluster is formed. And if P is a border point and no other points are density reachable from P, then you can move on to the other point. And if P is a outlier, then there is no cluster formed for that region. So that is how you can compute the clusters using the DBSCAN algorithm. Yeah, let's see an example now. These are the set of samples that are given to us, and the epsilon is given as selected as 2, minimum points is selected as 3. In that case, what we are doing is, for every object O in the given data set, we'll be classifying every object O as, if O is a core object, then what we do, so you need to identify all the density reachable objects from O and assign them to this cluster. If you observe here, we are assigning all these points to this cluster. We are selecting one of the element as the O, the object O, and we are assigning all the density reachable points to this cluster. And these points are not density reachable from O, and all the elements that are density reachable from the selected point O, they are all. So we are selecting one of the point O as a density as a arbitrary point, and then we identified all the density reachable points from the point P, point O, and then these objects will form one cluster. And there are no more objects that are density reachable from these points. And in that case, we proceed to the other point. Now let's proceed with the other point, and now we moved on to this point. This is the arbitrarily selected point, and there are no other points that are density reachable from this point. Then we leave it as an outlier, and then we proceed further and select one of the other point as a arbitrary point, and we find all the density reachable points from that point, and that form the other cluster. Now these are all the points that form the other cluster. Now if you observe, so this is one cluster, this is the other cluster, and this is identified as outlier. And if you can, we already discussed that the DBSCAN algorithm works very well with the noise or any arbitrary shaped algorithms. So now this is the input data that is given, and when you apply DBSCAN algorithm on this data, and the points are identified as the core points, border, and the outliers. If you observe, you are selecting any one point, and all the points that are density reachable from this point, see here, these are all the density reachable, right? Here also these are all the density reachable. So these are all the density reachable points. They are all identified as the core points, and which are not density reachable, and they are in the neighborhood of the core points, then they are the border points, and these are all the blue points are the border points, and there are some outliers also. The algorithm, this is how identifies or distinguishes every point as core point, border point and outliers depending on the density reachability. And now let's see some example. When you apply this DBSCAN algorithm on these shapes, if you observe, so there are different shapes, right? So how the type of parameters we are selecting will affect the final clusters. Just to understand that, we are using this example. So let's see. So here I am choosing the minimum number of points as 4 and the epsilon value as 0.5 and 0.4. In that case, so this is the data set and these are the final clusters I am getting, right? And when I change the data set, this is another data set, and when I choose minimum points as 4 and the epsilon value as 5, 3.5 and 3, in that case these are the clusters. So when I choose the first set of points, that is epsilon at 5 and epsilon at 3.5, these are the cluster I am getting, and epsilon at 3 I am getting this set of clusters. That is, it's very well understand that. So you can very well understand that. So the DBSCAN algorithm, the clusters produced by the DBSCAN algorithm are very much sensitive to the parameters that we are choosing. Yeah, now this is kind of synthetic data we have taken, different shapes, and then we have applied different types of clusters on this data. So if you observe the K-Means algorithm, so then affinity propagation, then mean shift, spectral clustering, Ward, then agglomerative, then DBSCAN and the Bitch algorithms. So if you observe on arbitrary shapes, even with the density regions also, on different types of data we have taken, and if we have executed different types of algorithms, if you observe on any type, the DBSCAN algorithm works very well on arbitrary shapes also. Right, so that is the effectiveness of the DBSCAN algorithm, and choosing the parameters is little hard, and for that we can use some techniques. So maybe for every nearest neighborhood you need to identify how many points are sorted according to the nearest neighborhood and plot it, and whenever you see this angular knee, then you can identify this point as a parameter. And another limitation of the DBSCAN algorithm is, of course we understand that DBSCAN algorithm is very much sensitive to the noise. In addition to that, another problem is when the data is having varying densities, in that case also DBSCAN algorithm fails to work. If you consider the data is having different densities, here it is too much dense, it is very sparse, but it should be identified as one cluster, and the dense portions are to be identified as another regions. And if you observe here, if I take minimum points as 4 and epsilon as 9.92, in that case these are the sets of clusters I am getting. So this is one cluster, this is another cluster, and all this has formed as another cluster. And if I change the parameters to minimum points as 4 and epsilon as 9.75, in that case all these elements, so except this is identified as cluster, this is another cluster, and rest of all the elements are grouped into another cluster. So that is how DBSCAN algorithm is much sensitive to the parameters, and also when the data is of varying densities, in that case also it fails to form the clusters. So in this lecture we have discussed two different partitioning algorithms and one density based algorithm. Under the density based algorithm we have discussed DBSCAN algorithm, which is very much robust with the outliers, but which is very sensitive to the parameters. So parameter tuning is very important in case of the DBSCAN algorithm. In case of the partitioning algorithms, we have seen what are the advantages, strengths and weaknesses of the K-Means algorithm, and how effectively Kmedoids algorithm is handling the outliers problem that is encountered in case of the K-Means algorithm. Yeah. So with this I conclude. Thank you for watching.